Hello and welcome to this second video of P2. We're going to look at lots of equations in this video, so you might wish to have your equation sheet with you. So in your exam you're given an equation sheet, but you're not given any units and you're not told how to put them into triangles. So what I would do is spend a bit of time memorising the units and memorising how you put these things into triangles, because it's going to make it a lot easier for you when you get into the exam and you're trying to rearrange things. And then sometimes you actually get marks for units, so if you know them it's worth putting them in. So first thing then, let's look at this equation. You're given the weight equation, and you have to be able to calculate weight, mass or gravitational field strength. Now weight is always in newtons, mass is always in kilograms, and gravitational field strength is in newtons per kilogram. Now to put this into a triangle, the two numbers that are timesing each other are going to go on the bottom, so mass and gravity, and your weight is going to go at the top. Now we'll try some questions. How much would a 60 kilogram person weigh on Mars with a gravitational field strength is 3.7 newtons per kilogram? Now notice I'm underlining my key points. I've underlined what I need to find out, and I've underlined what I'm going to use to find it out. So here I need to find out weight, so I'm going to cover up weight in my triangle, and that leaves me with mass times gravity. So I'm going to do 65 times 3.7, and I'll end up with a weight of 240.5 newtons. Now if we look at number 2, how much mass, that's the thing I need to find, would an object with a weight of 40 newtons have on Earth where the gravitational field strength is 9.8 newtons per kilogram? If I'm trying to find out mass, I'll cover it over in my triangle, and I need to do weight divided by gravity. So in this case I'm going to do 40 divided by 9.8, and it's going to come out at 4.08 kilograms. Right, last but not least, what's the gravitational field strength of Jupiter? So I'm trying to find out gravitational field strength. If I've got a 20 kilogram object and it weighs 5. Now we're going to look at elasticity, and we're going to look at the relationship between the force and the extension on a spring. So when a force is applied to an elastic object such as a spring, the force is stored as elastic potential energy. And when that spring returns to its normal shape, work is done to take it back to that normal shape, and the energy is transferred from elastic potential energy to kinetic energy. Now, each time you apply a force to a spring, it will want to extend. So if we look at Hooke's law here, this tells us a relationship between forces and extension. So when you apply a force to a spring, it might be that you suspend a mass off it, so you hang a mass off the end of a spring. Now, to begin with, the extension of a spring is directly proportional to the force being applied to it. So if I were to draw this as a graph, and I'll draw this up here, if force was at the bottom and extension was up the side, you should find that as one increases, so as force increases, so does extension. And this continues at a constant rate, so it's said to be directly proportional. However, there gets to a point where you reach the limit of proportionality. So at some point, no matter how much force you add to this spring, you don't end up increasing your extension. This is because you've extended the spring beyond the point of which it's directly proportional. So the limit of proportionality of the spring is exceeded. So there's a point that's reached where the spring can't physically stretch any further, and that's where its limit of proportionality lies. Now the spring constant can tell you quite a lot about a spring. If a spring is stiffer, the spring constant will be larger. So if you've got something that's harder to pull on, its spring constant will be larger. Now you need to be able to put this into a triangle, you need to be able to put the units to it, because this is how you're given the force extension equation in your exam. So the units are here for you. The forces are in newtons, spring constant is in newtons per metre, and extension is in metres. If we put this into an equation triangle, force is going to go on the top, and then the two components that are timesing each other are on the bottom as usual. So we're going to have spring constant times extension. Now if we try this with a question, what is the spring constant of a spring that extends from 1.2 metres to 3.4 metres under 60 newtons of force? So you're finding spring constant, you've got extension here, and you've got the force. Now there is one step you need to do before you can put this into a triangle. You need to get this extension value into a single value, because at the minute it's telling you where it's moving from and to, but it's not telling you overall by how much it's extended. So to do this, what you're going to need to do is take the final value of 3.4 and take away the initial value of 1.2, and overall this gives you your extension of 2.2. Now you can use this 2.2 using your triangle. You're trying to find out the spring constant, so you'd cover up spring constant, and then all you're going to need to do is your force divided by your extension. So here we've got 60, which is your force, divided by your extension of 2.2, and this gives you your spring constant of 27.3. Now whenever a force is applied to an object and it causes an object to move, work is done. Think about work as energy. Energy is transferred when work is done. So you're given this equation on your equation sheet, and first job I would like you to do is add your units to it. So work done, like I said, is just the same as saying energy transferred. So work done is going to be in joules. Your force applied is a force, that's in newtons, and then the distance is in meters. Next thing I'd like you to do is put this into a triangle. So two things times them together on the bottom, force times distance, and your work done is going to be at the top. And we've got 3 example questions for you to have a go at. So first one, calculate the work done. So after work done, right, I'll cross out work done then. When a force of 50 newtons is used to move an object 100 metres. So I'm going to have to do the force of 50 times by the distance of 100, and it comes out at 5,000 joules. Next one, calculate the force required. So I'm trying to find out force, so I'm going to cross out force. To move an object 20 metres when a person transfers 40 joules of energy. So I need to do here the work done divided by the distance. So I'm going to do 40 divided by 20, and it's 2 newtons of force required. Next one, now I'm going to move on to power. Power is defined as the work done or the amount of energy transferred in a certain amount of time. So if you have one appliance that is more powerful than another, it will mean in the same amount of time it would use more energy, or it would transfer more energy. Now the equation you need to be able to use for this is as so. So power, energy and time. But the units for this are quite different. Because you've got 2 sets of units that you could possibly use. Now it could be that you've got an appliance that uses watts, or the power is measured in watts. Now if you've got an appliance that's measured in watts, your energy transferred will always be in joules and your time taken will always be in seconds. However, you can also have a different set of units on the go. If you've got something that's measured its power in kilowatts, then instead the energy it transfers will be measured in kilowatt hours, and the time taken for this will be in hours. Now in both cases the same triangle applies, but you've just got to look at your units. So remember, there are 2 sets of units for the power triangle. Now the triangle looks exactly the same each time. Energy is going to be on top, and then underneath we're going to have power times time. Okay, so we're going to look at power calculations and applying the power triangle. Now for the first calculation, we're going to need to find out the power of a heater that transfers 60 joules of energy every 2 seconds. Now if I've got a value in joules and I've got a value in seconds, this power must be in watts. And all I'm going to need to do is use my power triangle. Now because I'm finding power out, I'll cover over power, and that'll leave me with energy divided by time. So I'm going to do 60 divided by 2, and it's going to be 30 watts, my answer. Now, next question, how much energy would a 5 watt light transfer in 1 minute? Well, I've got watts that I'm working in here. If I'm working in watts, this energy must be in joules, and the time has to be in seconds, but at the minute it's not, it's in minutes. So what I'm going to need to do first is times 1 by 60 to get my value of seconds. So it's going to be 60 seconds. So now I use my energy triangle, or my power triangle. So I'm trying to find out energy in this case. So I'm going to cover over energy, and that means I need to do power times time. So I'm going to do 5 watts times 60 seconds, and that equals 300 joules of energy. Now for my next one, calculate the power of a computer that transfers 50 kilowatt hours every 60 minutes. If I'm working in kilowatt hours for energy, I must be working in power or units of kilowatts. And I've got to be working in time units of hours, but at the minute I've got it in minutes. So let's think about what 90 minutes is as an hour. So there's 60 minutes in an hour, so if I had 60 minutes it would be 1 hour, but I've got 90 minutes, so I've got another extra 30 minutes. So that means I've got an hour and a half, or an hour and 30 minutes. Now, an hour and a half written in hours would be 1.5 hours. So I'm being asked to calculate power. So if we look at this top triangle, I've covered over power and I need to do my energy value divided by time. So I'm going to do 50 divided by 1.5, and then I'm going to end up with my kilowatt hours of 3.3 kilowatt hours. And that's my power value. Now for the final one, I'm going to calculate the time taken for a 10 kilowatt speaker to transfer 40 kilowatt hours of energy. Nice easy one, no changing of units, and I know that this time, because we've got energy in kilowatt hours, must be in hours. So to find out time, I'm going to do the power, energy, time triangle. I'm going to cover over time, and I'm going to have to do the energy, which in this case is 40 divided by the power, which is 10. And so I know that it takes 4 hours for that 10 kilowatt speaker to transfer. Now I'm going to think about gravitational potential energy. So gravitational potential energy is the energy an object has due to its position in a gravitational field. So this man here is about to bungee jump. Has got lots of gravitational potential energy because he's stood right on the edge ready to drop. Now to calculate gravitational potential energy you need to use this equation, and I've written in the units here for you already. Gravitational potential energy, because it's in energy, is in joules. Your mass is in kilograms, nice and straightforward. Gravitational field strength you saw from a previous question or previous equation on weight is newtons per kilogram, and your change in height is going to be in meters. So we're going to try this for this question here. The Earth's gravitational field strength is 10 newtons per kilogram. A bungee jumper travels 100 metres and has a mass of 70 kilograms. Calculate the bungee jumper's gravitational potential energy. Well, it's pretty straightforward. You just do 70 times 10 times 100 and you get 70,000 joules. Now, you might be asked to rearrange this equation. If you are, it's probably best to put it into a triangle first. Now, to put this into a triangle, you just need to put your elastic potential on top, and then the 3 components you're going to times on the bottom. And then whatever component you need to find, just cover it over. So let's say you need to find out the gravitational field strength of a planet, cover that one over, and then do whatever's left. So in that case, you do elastic potential divided by your mass times your height. Right, now we're going to move on to kinetic energy. So kinetic energy is movement energy. If you imagine that bungee jumper at the top of his cliff, he had loads of gravitational potential energy. Now, as soon as he actually jumped, this energy would have been transferred into kinetic energy or movement energy. So all these energies do link up. They all transfer to one another. The kinetic energy equation is as follows. So kinetic energy is measured in joules, mass is in kilograms, and speed is in meters per second. We're going to have a look at this question. What is the kinetic energy of a car that has a mass of 1,000 kilograms and a speed of 20 meters per second? So in order to calculate this, you need to do half times the mass times the speed squared. Now please, 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 if you don't have a scientific calculator, do this step first. So square your 20. Now to square a number, remember you times it by itself. So do 20 times 20 first, then do the rest of your equation. So it comes out at the answer. Right, now we're going to have a look at momentum. Momentum is the tendency of an object to keep moving in the same direction. So if you imagine you pushing a shopping trolley, once you let go of that shopping trolley, the shopping trolley doesn't stop, it continues to move. Also, the shopping trolley doesn't just change direction randomly, it continues to move in the same direction that you pushed it in. So you can calculate momentum using this equation here on your equation sheet. Momentum is in kilograms meters per second, mass is in kilograms, and velocity is in meters per second. And to put this into a triangle, momentum is at the top and mass times velocity is at the bottom. So if we apply this to a straightforward question first, so what is the momentum of a 5 kilogram object moving with a velocity of 2 meters per second? Well, you'd cover up momentum because that's what you're trying to find out, and then you're left with a mass times velocity, you're going to be 5 times 2, and it comes out at 10 kilograms per meters per second. The next one, what is the velocity of a 10 kilogram object with a momentum of 50 kilogram meters per second? Well, your first job is your calculated velocity, so you need to cover up velocity, and then you've got 10 kilograms, so that's your mass, and you're going to have to divide your momentum by your mass, because that's what you're left with trying to do. So something important you need to know about momentum is it's always conserved. And what I mean by that is the total momentum before an event, such as a collision, is equal to the total momentum after an event. And this can be really useful because you can use it to calculate things like the velocity of objects after they've collided. So I'm going to go through 2 examples now, 2 questions that I've seen in papers, and I think they're fairly standard questions. So by going through them, you should have a better understanding of how to use this curve of conservation of momentum. So the first question involves 2 trolleys, and we've got trolley A and we've got trolley B. Now trolley A has a mass of 8 kilograms, whereas trolley B has a mass of 4 kilograms. And trolley A is moving to the right with a velocity of 2 meters per second, whereas trolley B is moving to the right with a velocity of 0.5 meters per second. Now it's important to know they are both moving in the same direction, even though the velocities are slightly different because they're moving at a different speed. In some respects, the velocities are quite similar because they're moving in the same direction. Remember, velocity is speed with direction. So first thing the exam board asks you to do in this question is they ask you to work out the momentum of trolley A before the collision. Now to do this, you just need to do its mass times by its velocity, because you're just going to use this equation from the previous slide. Now that's going to work out at 16 kilogram meters per second. Then they ask you what is the momentum of trolley B before the collision, and again all you're going to do is its mass times its velocity, and that's going to be 2 kilogram meters per second. They then go on to say what is the total momentum before the collision. Now, the total momentum is going to take into account the momentum of trolley A and the momentum of trolley B. Now, because they're moving in the same direction, remember velocity is direction with speed, because they're moving in the same direction, you can just add these 2 momentums together and that gives you the total momentum. So you've got 18 kilogram meters per second. Now, the final thing the exam board often asks you to do is calculate the velocity of the trolleys after their collision, so the velocity with which they move off. So I'm going to put here velocity after. Now to calculate that, you need to take into account the fact that momentum isn't lost. It's always conserved. So you know, I'm going to put here before momentum. You know the momentum before the collision. You've got it here. It's 18 kilograms per meters per second. Now you know whatever the momentum was before the collision equals the momentum after the collision. Now how do we calculate momentum? Remember, we calculate momentum by doing mass times velocity. So do we know a mass? Well, yeah, we do, because we've got these 2 masses here. So we've got the momentum before the collision is equal to the mass, total mass, which is going to be 8 plus 4, which is going to equal 12, times your velocity. Now at this point, we can get this velocity after the collision on its own. We can rearrange this equation. So here, if we've got 18 before the momentum, we can take this mass value over the equal sign. And remember, whatever we're doing to it on one side, we'll do the opposite on the other. So we're going to do 18 divided by 12, and that will give you your velocity after the collision. And so that comes out at 1.5 meters per second. Next then, we're going to think about another way this question is presented. So this question could also involve trolleys, but trolleys moving in opposite directions. So let's imagine now that you've got the shopping trolley A moving to the right still, so that's still doing that, but shopping trolley B is coming to the left, so you're going to have a head-on collision. Now in this case, this changes the total momentum those two shopping trolleys have, because momentum needs to count or take into account velocity. Now if those two shopping trolleys are about to have a head-on collision like so, then this momentum A, which is 16, is going to be hit by this momentum, this 2 kilograms. Now, because they're moving 2 kilograms per meter per second, because they're moving in opposite directions, before we had to add them together to get their total momentum. However, in this case, for the total momentum, we actually need to take the smaller value away from the larger value, because they're moving in opposite directions. So the total momentum in this case will be 14 kilograms per meters per second, which then would lead to you getting different values for your velocity afterwards. So you just need to be aware that if your question shows you two trolleys or two cars moving in the same direction, you add the two momentums together to get the total momentum. But if something is hitting another thing, and it's a head-on collision and one is moving in the opposite direction to the other, you need to take away the smaller momentum value from the larger one